I'm an independent developer, and I've been working in Clojure for now more than 6 years. Since then, I have authored a couple of libs, and I also have worked on Clojure itself. And in this talk, I'm going to present some of the things that I associate with my learning of Clojure. So it's down the Clojure rabbit hole, but my own peculiar rabbit hole. And before coming to Clojure, I'm part of the 8-bit generation, so I grew up learning Logo, Basic, assembly, and so on. And just after high school, I was introduced to CamelLite. And CamelLite, which is, or was, a limited environment around what was going to become OCaml. And it was used for teaching purposes in France. And with CamelLite, I discovered functional programming. And it immediately clicked with me. I found it way more expressive and composable than objective-oriented programming. And sadly, when some years after I had to enter the industry, I had to do some enterprise Java. But around 2004, 2005, I read the pages by Douglas Crockford about JavaScript, and I realized that the thing that I've been copying and passing blindly from some forums on the internet was a proper language, and that you could do some cool stuff with that. It has first-class function, it even has apply. So I started to use it everywhere. I use it with Rhino on the server. And for simple business application, it was nice. And inside my team, we were able to get a better velocity or agility using JavaScript on the server side. Until one day, where we were tasked to develop a collaborative application. And this was collaborative and real-time, so highly concurrent. And JavaScript on the server for such a task is not the better fit. It's mutable everywhere, so it didn't end well. But anyway, after this failed project, I had some kind of checklist of the features I like to find in my next language. I'd like, obviously, to find a functional language. And I was still more attracted to dynamic than static type language. I'd like it to run on the JVM because I wanted to be able to use it at work with all the libraries to connect to any kind of big enterprise stuff or whatever. Well, to leverage the ecosystem. And having suffered from boilerplate, maybe surprisingly, I suffered from boilerplate more in JavaScript than in Java. All the hacks around fixing the broken scopes and so on. And so I really wanted something with metaprogramming capability. And last but not least, a good concurrency story. And at that time, I was really prepared to give up on some of these requirements. And one day, I stumbled on Clojure, which was around 3 or 4 months old, publicly. And it has all the features I wanted. So I was quite interested. I was thinking that it was too good to be true. And I looked a bit more. I kicked the tires of both the implementation and it was solid for such a young project, and also of the implementer. And I realized that this guy, Wichiki, has a clear vision of where he wanted to bring us with Clojure. So since then, I've stayed with Clojure. And to me, my experience with Clojure is quite close to this Zen proverb. I was at one point in my life where I was ready to learn new things. And Clojure and its community appeared right at the right time. So as I said before, I'm going to share some of these things that I've learned along the way of learning and working with Clojure. But I am going to do that in a manner which is close to free association, because I kind of rely on a lot of intuition. So my thought process is usually this one. Well, exactly, it's maybe a bit more divergent, like this, or even that. But we get the idea. So don't try to find a whole coherence to this talk. It's more like a bit of ideas or perspective that I have explored or that I wished I could explore. But the first thing that I learned when I came to Clojure, because Clojure was my first Lisp, it was the parentheses. And parentheses, despite the bad names that they have, the bad reputation, they are not that hard to grow and get accustomed to, unless you are focusing on arithmetic. Because obviously, when you switch from infix to prefix, it's going to be quite different. And you have a bit more time to get accustomed to this ordering. But for the rest of the code, it's just a matter of moving the left parent from after the function to before. So it was really not a big problem to get accustomed to parentheses. And then I realized that the reason behind being a Lisp was really purely pragmatic. When you design a new language, if you choose to be a Lisp, you don't have to spend your time designing a grammar for this language. And not designing a grammar for this language leaves the language open. Because if later on you want to add some feature in the language, you don't have to find a loophole in the grammar to add the feature. And being a Lisp also gets us some nice properties like metaprogramming and serialization nearly for free. And it's quite an interesting package for little effort. So from an engineering point of view, it's quite a pragmatic decision to go with a Lisp. But under the hood, the programming model of Clojure is different from Scheme or Common Lisp, because it's really functional first with persistent, immutable data structures. And persistent, immutable data structures were really a new thing to me, because when I used Camel, there wasn't the persistent data structure. You only had some type that you constructed, and the only persistent data structure back then was the list. And so for years, I really wanted and wished that there was something like persistent data structures, but I wasn't able to find them simply because I didn't use the right word in the search engine. And anyway, when I discovered Clojure, I discovered that persistent was the word that I've been looking for. But I have a small riddle. What is close to a persistent data structure and that we have learned in elementary school or even before? Numbers. When I read this book, the main takeaway for me was was that it gives a framework to think about data structures as numeral systems. And there are some interesting mapping between the two. It really helps to get an intuition about how a persistent data structure is going to work. So for example, if you have a unary representation of a number, it's close to a linked list. Because when you add something to a list, you simply create a new cell at the front. And when you increment a number written in unary, you simply add 1 at the end. That's all. And if you want to look up in a list, it's going to take you a linear time to perform the lookup. And if you want to compare two unary numbers, it's going to require a linear time too. While if you want to compare two numbers written in base 10, for example, it's only going to take a logarithmic time. So it's really the same idea. And I don't know whether you use this kind of material when you was in school. Here, the small plastic cubes, the smallest one, the yellow ones, are units. And when you have 10 units, you can exchange them for a green bar, which is a 10. And when you have 10, you get a light blue square, which is 100. 10 make 1,000, which is the red cube. And the random access list, a persistent random access list, is exactly that. You start by accumulating items one by one up until you have enough. Let's say enough is 10. And when you have 10 items, you convert them into a bar, a group, and you put it aside along with other bars. And when you have enough of those bars, you group them again and put them aside with the other groups you have already made. And this go on and go on and go on. And it's really the same thing. Adding to such a collection is really the same thing as incrementing a number. And so we quickly realize that when we increment a number, in bad cases, when all you have is 9, the carry is going to propagate all to the end. So in this case, the cost of the increment is going to be logarithmic in the worst case. But in the best case, when you have anything but 9 to the right of the number, is going to perform immediately. And then to devise new kind of data structure, you simply tweak the numeral system, the way you write number. Maybe you can introduce a new digit to represent 10, such that you can buffer the carry and delay the propagation of the carry, so as not to pay the propagation, the whole propagation through the whole data structures at only one time. And this is kind of a recipe to create a data structure. Tweak a numeral system, convert convert it to a data structure, and you get a persistent data structure. It works nearly every time, but it doesn't always get us something interesting. For example, I'm not sure that Roman numerals are going to give us interesting data structures. But something more interesting and more complex is finger trees. Finger trees can be thought as numbers too. And a very twisted way to write down numbers. You have 4 digits, 0, 0, 1, 2, 3. But 0 and 1 are only allowed on the most significant digits. Everywhere else, you have only 2 and 3. And to make things a bit more complex, the most significant digit is not the digit which is to the left, it's the one in the middle. Because this representation is symmetric. You can increment either by the left or by the right. So you have both unit digits at the end, and then you converge to the middle, where you have the most significant digit. So it gives that you have those weights for each of the digit. So if we take an example, we start by 0, the empty collection, and we are going to add items by the right. So easy, 0 plus 1, 1, 1 plus 1, 2, 2 plus 1, 3. Here, it gets a bit more interesting. 3 plus 1 is 4, but 4 is not a digit. And you can't, you know that now you need to have 3 digits because of the symmetry. You always have an odd number of digits. And the unit digits can be only 2 and 3. So the only valid representation for 4 is this one. And then you continue adding to the right. So you increment the right part of the number. And here we have a carry, which is propagated to the next digit in the direction of the most significant digit. Remember, it's at the center of the number. And you go on, you increment the units, you propagate a carry, you increment, you propagate, you increment, you propagate, but here again, you overflow the most significant digits, so you make a 4 in the middle, a 4 being 2, 0, 2, and you continue doing so. Yep. So the interesting property is that despite the fact that we have always added the elements to the right of the collection, or rather incremented the number by the right, the representation that we get at the end is balanced. We don't have a lot of 0 on one side and all the items on the other side. So the structure is balancing itself automatically. And we can check that we can dequeue. And for example, we are going to take the same number and decrement it this time by the left. So the first step is a bit bizarre because we want to decrement 2, but you are not allowed to have a 1 anywhere else but in the most significant digit. So since you can't decrement the 2 to be 1, you have to borrow from the next digit. But the next digit also happens to be a 2. So you need to borrow from the next one, which this time is the most significant digit, is 1. You decrement it to 0, and you can borrow from it. And that's why you get 3, 3, 0, 2, 3. By the way, 22123 is the representation, is one representation of 17, because we have performed 17 increments on it. And after that, you can decrement. This one was easy. This one too, because it's just borrowing from the next digit, and so on. Here, there's a special case, because in the middle, we have 202, which is 4. And so borrowing from 4 gives us 3. That's why next time we have 3. This 3, 202 minus 1 gives 3, and the 3 which results from there. And then you can continue performing that. It may seem bizarre, but once you have done it a couple of times on paper, it's rather easy, and it gives a good intuition on how finger trees work. So you go on, and at the end, after 17 decrements, you are back to the empty collection. So the model, or the simplification of data structures, seems to work. And it's really something which I find very powerful when trying to understand a new data structure. Well, back to something a bit more pragmatic, and how we use these data structures in Clojure. Having dynamic and persistent data structure, we are able to have some kind of low ceremony modeling. By that, I mean that when you start a project, at the point where you know the least about the domain, about the problem, you can get away by not over-engineering your modeling. You can even borrow the model from whatever comes over the wire or from the database, and take that as the starting point. And because most of the things that you get from either a database or message, whether it's in JSON or XML or whatever, it's quite easy to map it to vectors and maps in Clojure. So mapping from external data to inner values is not that hard most of the time. And you can start by just having one model from your whole application, one way to represent the data. And if you want, you can consider that as having not one model, but several identical models. Now, this interesting is, as you go through the project, you get a better understanding of how you should structure your program. And at this time, you want to evolve your model. But since everything is immutable and is just plain data and has no behavior to it, you can simply write converters from one model, one representation, to the other. And the isolation is done like that. You can really introduce and devolve new parts of the application simply by converting the data in and out of the module. And it's really liberating, because it allows some kind of loose coupling that at first you don't want to allow you, because you think that it's the same thing as having one object coming straight from the database and through the whole layer to the presentation. But it's not the same thing, because in the case of objects, we are not carrying only values. We are also carrying some behaviors. We are importing code from one module to the other, creating dependency between them. Here, the only thing that is shared between the layers is a common understanding of a schema, of the way values are represented. That's all. There's no code sharing which is implied by the use of values. The coupling is that at first I feared, and that I imported in some way from my previous experience, was really tied to behavior immutability. Once you remove them from the equation, it's safe to pass the same thing from one end to the other. It's just a message. It's not harmful. You can transform it. You can emulate it. It's quite easy. And also, the dumber is better. By that, I want to mean that the less interesting your collections are, the less they require from the other part to consume. For example, if you have a plain map or a sorted map with a custom comparator, then the custom map is going to be a bit more difficult to deal with on the other side, because you need to share the comparator with it, and maybe the other side is written in another language which doesn't have the equivalent data structure. So the more you want loose coupling, the more you should try to use plain and dumb data structures. And getting rid of behavior and immutability makes also encapsulation nearly useless. When in object-oriented manner, you have encapsulation to protect direct access to the field, and you put everything behind methods. It's only because you want to preserve invariance between the fields. But when you are immutable, if you have one value, either this value is valid towards the invariant, and since it's immutable, this value will continue to be valid for the rest of its life, either this value is invalid. So the way that you build the value has no interest, is no business to the consumer. The only thing which is interesting is that the value is valid against the invariants that matter to the consumer. So that's why it's very important to have validators. And in Clojure, we have validators on all the reference types because of the safe publication pattern. When the reference type are one means of communication with other modules through shared memory. And by putting validators at the core of reference type, you are sure that you won't be able to publish something which is not valid. So at the publication time, at the moment you make your data available to the other, it's going to be enforced that the invariant holds. And this makes me think about postal law. Postal law say that you should be liberal in what you accept. it should be taken with a grain of salt, because by being liberal, if you are liberal and you have sloppy producers of data, then you are going to give them bad habits. Basically, your liberalness in the way you accept data, broken data, is going to define a de facto new notion of validity for this piece of data. And then it's going to be hard to evolve, because this definition of what is a valid or rather a nearly valid value is maybe a bit fuzzy. It's just a consequence of an implementation detail of your code. And working, reverse engineering your own code to understand precisely what you have allowed is going to be kind of an headache. At the web scale, we have seen this kind of things with HTML and browsers accepting broken HTML. And then when it has been time to define what was proper HTML, it was quite hard. And it's only in HTML5 that we have a processing model in the specification that says how to react to improper HTML. So it took up to HTML5 to describe what was the liberal part of accepting that. And this definition has been done by reverse engineering the behavior of all the browsers. So most of the time, you don't want to do that in your own project. So avoid to be too liberal in what you accept. Anyway, so as I said before, using values, plain old values with just map, vectors, simple numbers, not anything special in them, give us a good modularity and very low coupling. Such a low coupling that it's it's more easy to transition from an internal module to an external service. I'm not saying that it's super easy, just easier. Again, because the dumber your message is, data structure-wise, the easier it's going to map to, let's say, JSON. And this leads us to a common refrain in the Clojure community, and that is that data is the API. When you define a library in Clojure, you often spend more time crafting a schema from some piece of data than writing the function. For example, the ring library, which is used to perform synchronous web development. At its core, its value is in the spec. The spec says how to map an HTTP request or response to Clojure data structures. And from that, you can work with all the tools that you have by default in the core libraries or in any other library. You are not tied to using only things that come from Ring. It's just plain old data structure. You can reuse everything from everywhere because you don't use special code, which would then be only whose objects or types would only be understandable by libraries that transitively knows about Ring. But data as API has a blind spot, is that when you have only dumb data in your message, in your values, your process, how things are chained together, it's not part of the data. So it must be fixed, and it must be agreed upon by all the parties. All the modules must agree on how everything is going to be chained together. So it's a shared understanding, but it means that the process is closed. You can't evolve the way things move through your system without updating every part of it. And this can be avoided simply by sharing behaviors, by putting behaviors back in the values. So basically, it simply means that by putting a function inside a map, you can say to a module, OK, when you are done doing your stuff, call this function. Or in case of emergency, call this function. You can say that if you pass the function. If you are not allowed to pass the function, all you can do is pass a keyword, maybe, saying in case of emergency, do one of the three things that we have all agreed upon that can be done in case of emergency. You see, it's when you can pass a piece of behavior, it can be anything, and you can evolve later on to react on to new requirements. While when you only pass keywords or simple values, you have to plan ahead and let all the parties know about the different cases that are possible. And another riddle, how do you call a system that sends data and the process inbound with the data? It's called a web server. HTML, again. HTML is data, the content, and process, links, forms. They define what the client, what the consumer is going to be able to do next. So you have both the data, and you also have some action that you can perform to progress through the application. And you can do that because the client is made of two parts. It's made of a general purpose client, the browser, which understands those annotation, how should I perform, what should I perform when the user clicks on the link, or when he fills a form. And the other part of the client is the mid part, the user in front of the computer, which is going to perform the business logic. It's going to scan the page, find words, understand that in this field it must put this value. And this is the kind of behavior which may be interesting to bring to our simple data. If we look at a form can be understood like a pointer to a function somewhere. Then you have some details on how to invoke this function. Because basically a form is just an implementation of the invocation protocol. So here it says that to invoke this function, you have to post through HTTP to this given pointer, and you have to craft a payload which is going to be URL encoded and which has some value in it. It's like saying, it's a bit like saying, hey, you need to call this function in memory, and you need to put this value on the stack and this one in this register, and when you are done, call it. It's pretty analogous. And then with the hidden fields, we can even have some kind of closed over environment. Things that the form has bring with us from the server, from the producer. So basically, a form is a form of Clojure. Not all Clojures can be serialized or seen as a form. But a subset of Clojures may be amenable to being serialized as a kind of forms. So maybe the solution to this problem of sharing behavior is to have something like hypermedia. Currently, there's kind of a Cambrian explosion of format around hypermedia, but with no uptake, and they are either too simple or too complex. HAL is not bad, but it's mainly read-only. It doesn't provide anything powerful enough to perform updates. So maybe it would be interesting to design a kind of hypermedia format by taking a look at the kind of closures which could be good candidates for form-like serialization. Basically, what we need is just some kind of partial application. If we go back to that, the hidden input can be seen as the partial application of the function where you have already provided the secret argument. So maybe trying to reduce the scope and only consider functions which have named arguments, and then to only consider the partials that you can derive from those functions, and maybe allow for renaming and renaming the arguments would be interesting, and it would be quite easy to serialize that in a straightforward manner, because basically it would just be a mapping. So this name becomes this name, and default values for the values that have already been applied through partial, provided through partial. But what's we gain already through all this stuff? Well, in such a setting, when you ask for a piece of data to a server, or maybe you get it over a queue, and you get a piece of data, instead of having this piece of data out of context and not being able to do anything with that, but what you know that you can do with the tools that are on your side, that you are going to be able to look at any part of the data, but you don't know how you are going to perform anything that involves with the process. Because again, the process has to be agreed upon. What should I do with this piece of data? What should I do next? It has to be agreed out of bound. But if you have this kind of annotation in the data, then you gain the ability to dynamically introspect, introspect what you can do to, or rather what the rest of the system can do with this piece of data. So from a user point of view, the experience would be really like being at a REPL, getting something and being able to know which protocol, which generic functions are implemented, are available upon those data. So let's pretend that it exists. And I didn't even bother to find a serialization. So you have the plain data, and then you have the closures, which are or would be serialized. Then the generic part of the client could simply remove those keys and map them to generic function implementation for those data, so that calling the generic function delete on any of the item of the to-do list would trigger the operation serialized behind the delete. That is, it may trigger a post or an HTTP delete, or it may even trigger a message to be put on a queue. Well, anything that your client can support in terms of transport and invocation protocols. But you describe what to do next. The general purpose client map those abilities to generic functions. And from your point of view, you are just dealing with generic functions which are polymorphic over what you get from the wire. So if you know some function and that you, by introspecting a piece of data, you see that you can use it, well, you can use it. You don't have to constantly look at the documentation to know what you can do next. It would really bring introspection to this kind of programming. Obviously, if you want that to scale, all names should be namespaced. And it's a shared understanding of common needs that would allow to have some largely used generic function, maybe for things like adding to a collection, basically what is covered, for example, by the Atom protocol. The Atom protocol is in some way the hypermedia specification of a list or of any kind of sequential collection. It allows you to add and remove from the collection. So again, the benefits within that we would have almost no coupling or as low coupling between the producer and consumer than the coupling we had before when we are just exchanging data. But on the upside, now the topology of the process has not to be shared. It can evolve dynamically. You can roll out new services and have them consume old services. You can have old services consuming new services without having to register them. They would simply discover each other through pointer traversal, like we do when we are in only one process. So to me, it could really help to bridge the difference of experience that we have between dynamic programming in a single process and programming with other remote services. Last thing, once you know how to serialize those kind of limited closures, maybe it's interesting that you can pass them as values to other services. So you can have some kind of higher order services, sending description of services to invoke to other services for them to invoke. So basically allowing to have a flexible way to acknowledge for the end of a long process. You would send as an argument a Clojure, or a form. It depends on the way you want to look at it. You would send a Clojure to the other process, to the other service, a form describing what to do when the job is done. And so notification of the job being done is now dynamic. You can choose that you want to receive the notifications through AMQP. Maybe some other service may choose to receive the notification through a direct HTTP connection to a specific endpoint. It leaves all options open. Some services may even elect to not receive a notification at all. It would allow for probably more flexible and more dynamic systems. Of course, I have done a lot of abusive simplifications, and I have used Clojure for endpoints because, after all, nothing that I have described makes synchronicity or asynchronicity required. So it can be messaging, it can be a synchronous request, it doesn't matter. But anyway, as long as you can address and describe in some way, provide a template of how to create a payload, then that you can safely share it between services, you gain a great more flexibility. So back to real Clojure now. Computation in Clojure. Computation in Clojure has been usually done through sequences. Sequences is or rather was the default iteration model. When you want to process something, you first turn it into a sequence, and then you use all the sequence verbs to work on that. And superficially, sequences could be confused with collection. They are very similar to collections, to the point that some collections verbs work on sequences, but they are not the same thing. Sequences really are computations. They are reified computations, and they should not be kept around for too long. They should only be used to perform the computation. If you want to keep whatever is in a sequence, you'd better put it back in something more concrete. So basically, a sequence has to be thought like a pipeline. You have a concrete data source, or maybe several. And through sequence processing, you are going to create something else which is concrete, or say defects. But you are not going to keep the sequence as a collection of results in memory. Yeah?
So you're saying that the sequence is basically the way you specify how you traverse over a structure. It's not.
Yeah.
It's not the structure itself. It's
yeah.
traversing.
Yep. And so it was the original way to compose computations. And when you start to work with sequences, you quickly start to think about indices as a kind of code smell, because indices, that is direct lookup into a structure may look efficient, but it's efficient only because we choose data structures that are efficient for lookup, because we are too accustomed to lookup. And for example, with persistent data structure, a vector is in fact a tree. And when you access each item by index, by incrementing the index, you are performing a full tree traversal at each access. When you traverse the vector using a sequence, you stay at the level of the leaves. And indices being a cut smell bring me to one of my favorite pet peeve, strings. Strings. We have nice encoded strings like UTF-8. But then we convert them in memory. And many runtimes use UCS2 for in-memory representation. That is, they consider that strings are made of cores which are 16 bits. And in truth is that cores are not even characters, because characters can be made of 2 cores. So the promise of direct lookup isn't even correct. But anyway, we are wasting a lot of space simply because of space and of CPU, simply because we copy this copy and decode the string to this car array. And by doing so, we are a bit more correct, but not totally correct, because UTF-8 was not indexable because of the varying length encoding, but UCS2 is not, because some Unicode characters require 2 cores, 2 code points to be represented. So the length of the array is not going to be the length of the string in terms of Unicode. And if rather we had an abstraction which used cursors to simply start from one end of the string and move character by character, it would be more efficient. In this case, we would be able to work with plain encoded strings without having to decode them and copy them to another chunk of memory. And most algorithms, I'd like to have a counterexample. Most algorithms don't require you to be able to jump straight in the middle of the string. The only algorithm that I can think of that are interested in skipping part of that for performance because they want to achieve sublinear performance are things like Boyer-Moore. But even then, you would be able to use Boyer-Moore at the byte level. Simply, instead of searching the strings at the character level, you search it at the byte level using the encoding of the string that you search. And it worked. You can compose the encoding and this kind of algorithm. So it's really something that I have also tried to explore in Enliven. Enliven is a library that I'm working on when I have time. It means that I haven't worked on it nearly for 1 year. Anyway, it's a templating library. And I have explored in Enliven the ability to compose the encoding with the templating itself. So the static parts of the template are pre-rendered as bytes and not as as characters. And when you do that, you can pre-render them directly as byte buffers, which would be more efficient to send over the network. You won't have to perform one more copy to send them. And I also tried to compose that with gzip, so that static parts are already pre-gzipped, and you can chain that together. So it's interesting, and it worked. My work with gzip was really naive, and it wasn't that interesting. But then, more recently, I tried to put out the same trick for writing JSON. And so in JSON, you write directly compressed JSON. And it avoids you to emit field names again and again and again. Because when you think about it, you have field names in a JSON. And it's going to be repeated several times through the JSON. And you write those bytes down to a stream many times, each time. And then you have gzip, which takes the stream and tries to find the similarities. So it tries to find the back references to locate them. If you compose them together, you can simply say, hey, this is the same field as last time. And then you just emit a back reference straight to the last time. You don't have to emit to the output stream each byte. And then you can generalize that to any kind of repeating information inside your JSON, including strings which are in a similar manner. Let's say strings which are URLs and all start by the same prefix. Then you can declare a template, and instead of outputting the full URL each time, you say, hey, use the template URL with this parameter, and then underneath, JSON is just going to emit a back reference to the common parts of the template and put only the missing part in the middle. And this one is nearly done. So it's lacking on documentation, but it will be on GitHub soon. Anyway, recently I've been a bit bugged by all the inefficiency that we tend to forget in our stack. And there's a lot of unnecessary copies and allocation going on. And most of the time, by using composition, by postponing the computation as much as possible, we can get better efficiency. And this is the path that has been trotted to in Clojure itself, where we start with sequences. Then we try to mitigate the overhead of sequences by using chunked sequences. And then we try to remove the overhead altogether by switching to reducers as the new way of iterating over collections. And then now to transducers. It's the same pattern of avoiding to create intermediate data structures. Only create a big compose function, but in a manner that from the user, it still feel like it's dealing with concrete data, but in fact is creating a big compose function that will be run in one go without creating too much intermediate garbage. There are other efficiency stuff that I'd like to explore, but that I haven't had time so far. It's GPUs and cache oblivious data structures. Who knows about cache oblivious data structures? Okay, so basically cache oblivious data structures are data structures that are optimized to work well with any kind of cache hierarchy without knowing the number of level in the hierarchy, and without knowing the size of the cache block at each level. And it tries to minimize the cache miss that you perform during regular operation. That's very, very interesting. Basically, you can compare that to B-trees, which are used for databases and that were often sized in a way that one node was one block, so that you limit the I/O, but you have to know or tune the sizes of the node to match that of the block. And since it matches this size, it's not going to match the size of, for example, the CPU caches. And the cache oblivious data structure, by being recursive in their layout, gives us this property that it's going to fit well at any level of the cache hierarchy. Other things that I have discovered by working with Clojure is that ordering is harmful. There are many places where there is a real ordering, there is a dependency, there's a causality between two things. But most of the time, we have an ordering which is just incidental. But since the runtime beneath executes everything in the specified order, you can't reason easily. For example, when you have deeply nested ifs, then when you consider one if, you can't consider is expression alone. You have to take into account all the others to really understand where you are. And so refactoring a big nasty if is hard. And you have always to be careful when refactoring short-circuiting and or you can swap. You can't always swap the tools, and even with pattern matching, where the order matters. For example, you may have one pattern which checks whether the first item is 2, and don't care about the second, and the next pattern which don't care about the first item, but check whether the second item is 1. Then changing the order of the clauses in the pattern matching is going to yield different results for the input to 1, because for one order it will be the first clause which will be encoded order first, and for the other order it will be the second one. So there are several problems with short-circuiting. So you can't reorder easily. And the compiler can't do that because he promised to do things in order. So you are stuck with that. But you find the same thing with regexes. Regex are ordered 2 in their choice. So it's a bit surprising, but you always have to put the longest match to the left. Otherwise, you have this kind of result where AB is never matched. And when the two sides of the pipe are more complex, there may be no good order which will result in the longest match being always matched. And there's also the same problem when you naively transcode a CFG, a grammar, to a recursive descent parser, because when you do naive recursive descent parsing, you are going to try first one branch, and if it fails, you are going to try the other. And you may think that it's going in the end to get the same result, but no. If you have this simple grammar, which is pathological, but which makes the point, for a fully declarative parser, it's going to match any string with an odd number of A. But with a naive recursive descent parser, it's going to match nearly power of 2 of A. So it's not going to match the same set of strings. It defines quite different languages. So well, the consequences of ordered choice is hard to reason about. And again, by reversing the ordered choice, in this case, the behavior of a declarative parser hasn't changed, but this time the recursive descent parser is going to stop there. And we can find the same kind of problems in mini-kernel or Clojure, where the order of the clause to a disjunction or a conjunction matters. In Clojure, it only matters for conjunction, but for conjunction, it's still a problem. When you try to order your clause, there may be no good answer that is going to guarantee you that your program is going to find answers. Even if there are answers, it may be stuck in a branch with no answer in an infinite part of the space, of the search space, where there's nothing to be found, but it's stuck in that. And there's no good solution for fair conjunction in Clojure or mini-kernel. And that's also why in Prolog you had the impure operators that allowed you to quickly abandon the exploration of a part of the search space, but there were impure operators. They were denying the declarative nature. Answer set programming is really pure, but it's kind of unusable for small problems. And I will think that declarative can be summed by 3 properties. Associative, that is that there is some ordering, which is essential to your problem. But this ordering is not going to naively derive the execution. So execution may be parallelized as long as the global ordering is correct. Commutative too, because by default, ordering shouldn't matter. The order in which you specified your clause, your command, everything shouldn't matter. And last, if you repeat yourself, if you say the same thing twice, it shouldn't be considered as a problem. It should be just left as a letter optimization to factorize this away. And I try to apply this kind of acid in practice. And by the way, in distributed systems, with CRDT, for example, they use the same acid properties. And I tried to design Enliven following these principles because the predecessor to Enliven, Enlive, suffered from ordering everywhere. And it turns out that not only it's easier to reason about a template in Enliven because you don't have to understand what the user clauses has done before you, because everything is going to happen in parallel, and that the system, that the runtime enforces that there won't be any conflict. But by being more declarative, the runtime is able to leverage more information and to optimize it more deeply. So in my preliminary testing, outputting a template, HTML template rendered from a model was as fast as printing it, just using print in the REPL. And it was way faster than any other templating engine. Clojure templating engine. I haven't benchmarked against others, and that was only by staying at the string level without even trying to use the byte rendering stuff and so on. And an interesting consequence is that the design tend to be point-free because it's the easiest way to achieve, or at least it's the easiest way to achieve these properties that I have found. Despite my original style being not very point-free, I discovered that if I wanted to be able to leverage those properties, I had to be point-free. And so some little things that I will just mention is that when we talk about state, the real danger is the local state. That is the state of your environment. What is on the stack? What is in the registers? All this stuff that is not modeled, that you haven't designed. This is the kind of state which make some features like migration from one process to the other or snapshotting, which make them hard because you don't know what's on the stack and you don't know how it has been laid out because it is the job of the thing below you. And it's kind of dual, but writing very small interpreters or VMs is quite fun and can give you nice way to experiment because you can easily have some kind of very small VM with 4 operations, with very specialized to your stuff, and then be able to snapshot it at any point or have it explore all the alternatives. And so it's really interesting at the time, but that's all. I think my time is quite over by now. So thanks for listening, and sorry if it was fuzzy and very free associative, but it's the way I think. Questions?